Our next speaker is Cyril Boesch, and he's going to present a talk entitled Unifying Physical Backpropagation.
Maybe I wait one more second.
I'll ring the bell one last time, okay? Work. Floor is yours.
All right. So thank you, Clara and Florian, for putting this together. It has been very entertaining so far and giving me the opportunity to talk. So I will be talking about unifying physical backpropagation. This is work I did together with Yiğitan Gedit, a PhD student of Hakan, and then Ryan Adams, my advisor. So what do all those papers have in common, in addition to being mostly published in very nice journals? They all, in some way or another, compute a formally exact physical gradient method. Some have experimental implementation in optics, in mechanics. Some are more theory with Hamiltonian systems in general. But they tend to have different language, use different terminology. And so what we set out to ask is whether we can unify all of those under one umbrella. But before I go there, I want to start with a personal note. So a couple of years ago, I actually studied geology. And these are two pictures from a field trip in southern England. This is at a copper mine. And here you can see me taking a very bad picture of a granite with some interesting minerals. And as a length scale, I'm using a carrot. So you can guess I was probably not a very good geologist. And so I started to pivot. And my first station in my pivot was actually doing a PhD in a seismology lab. And so what do seismologists do, among other things? They try to figure out how the Earth looks in the interior. How do they do that? They build massive numerical elastic wave propagation solvers with which they can generate synthetic waveforms that propagate around the whole globe. And then they compare it with observations from earthquakes. And then they build a loss function, and then they try to compute gradients to minimize the distance and update the internal parameter of the Earth until this convergence, and then this is an image of the interior of the Earth. And so these are massive models, in this case with like 1.5 trillion elastic modulus density parameters that they invert for. And so they better have a good and fast way to calculate the gradient of this loss function, and they do this with the adjoint method. And so what I set out here is to use the adjoint method to unify formally exact physical gradient methods. And along the way, I will sort of come up with sufficient conditions under which you can obtain the adjoint field in the same physical hardware. And I will make this precise in a second. So to make this clear, this is not about approximate, coupled, or heuristic learning rules. I also don't consider learning rules that require augmentation of the state space. And this is only about calculating the gradient, how the parameter update happens, for example, in a self-learning way or in a teached way. This is not of my concern. So here is some symbolic neuromorphic platform. You have some input on the left side. The field propagates through your neuromorphic device. You record it, and you also record it at the output. I will use a projector to project onto the output degrees of freedom. Then you calculate some loss function that measures the performance of your computation, and then you backpropagate what is typically known as the error signal, or in the adjoint literature, it's the adjoint source. And so when I say I want to use the same physical systems, the only changes that I allow are changing sources and initial conditions. And if there are any explicit time dependence, I assume I can control them from outside and I can play them in reverse. So what systems do we cover? First, let me make an example and apply this to real-valued autonomous first-order system. We have generalized this to time-dependent system, non-autonomous system as well. And the main organizational principle is distinguishing between linear and non-linear systems, which will give rise to different conditions and algorithms. So in the adjoint method, you first formalize your optimization problem as a constraint optimization problem. So you have a loss function chi, and you optimize it over some parameters p, and u that goes into the loss function has to satisfy a certain ordinary or partial differential equation. So here f is, so this is an overdamped equation of motion. F is some potentially nonlinear forward operator. You may have some external sources, and initial condition, you integrate from 0 to capital T. And, sorry? Small f are external sources, external drives. And here the loss function has two terms. So it has a trajectory loss. So when you want to sort of encode things in full trajectory, compare full trajectories. And then it has a terminal loss where you want to learn, your system shall learn to end up at a particular location after the integration time. So the adjoint method relies on solving another ordinary differential equation that is derived from this one and somewhat similar. It also has one time derivative. The forward operator also appears, but is linearized and transposed. So this is the Jacobian of the forward operator. So the adjoint equation is linear. And now as sources or external drives, you replace the external drives you had here with the derivative of the trajectory loss. So trajectory loss gives rise to a source in the adjoint problem, whereas a terminal loss gives rise to initial condition for the adjoint problem. So how would we use the adjoint method digitally? So first we would solve the forward problem, record u, then we would evaluate the cost function, then we would calculate this adjoint source and adjoint initial condition, and then have another solver that solves the adjoint equation. Once we have the two fields, the forward and the adjoint field, we can calculate the gradient as the overlap between the adjoint field and the parameter sensitivity of the forward operator. So let me make this specific, make an example, and show how a local learning rule emerges. So for example, let's say you take two coupled Duffing's oscillator, linear coupling, some linear stiffness, and some Duffing nonlinearity. So the physical parameters wish to optimize are those stiffnesses and Duffing coefficients and couplings. And so let's take an example where we calculate the derivative of the forward operator with respect to, let's say, the first linear stiffness. So this is very sparse and only depends on what U1 is doing. And so now you can see how a local learning rule emerges. So the gradient is now just basically this integration between the adjoint field and the forward field at this particular degree of freedom where you want to calculate the parameters. If it's a coupling parameters, you will need both coupled fields. So now we can formulate the question a bit more precise. So what we're actually asking is not how to physically calculate the gradient, but we ask under what conditions can the adjoint field be obtained in the same hardware. And so this is the result for linear overdamped, so first order system. And you see, for first order system, and you see there is sort of two very distinct cases. So there is linear and there is nonlinear. And as we will see in the linear case, what you require is reciprocity, whereas in the nonlinear case, actually you need two conditions. You would need term reversal symmetry, which you don't have here because this is overdamped, and you need this symmetry of the Jacobian. And so let me walk through these two cases. So in the linear case, you have F, the forward operator, is just a stiffness matrix which is symmetric times U. And so this is the forward equation. Now when you look at the adjoint equation, they are actually exactly the same, except that you replace the external force with the adjoint source, so with the derivative of the trajectory loss, and the initial conditions with the derivative of the terminal loss. So that means that the same hardware that can implement the forward pass can also implement the adjoint pass. And why is this the case? This is the case because the adjoint field is also overdamped. So the forward system is overdamped, the adjoint field is also overdamped. And so how would we then run this physically? So we would first run the forward pass, record it. Then we would calculate the adjoint source and initial conditions from the loss function and run the adjoint source and record it, and then compute the gradient locally. Now, importantly, there is no infinitesimal notching. It's a single experiment to get the adjoint field. There is no difference of trajectories. It's just the adjoint field is just one one pass, and there is no time reversal required. This is over-damped dynamics, and yet you can learn full trajectories, not just fixed points. So now, when we go nonlinear, let me try to explain what is the obstruction here. So let us assume that the Jacobian is symmetric, so F is derived from an energy. Then the Hamiltonian echo backpropagation from Florian, and then there is also a paper by Maxence and Proussel that have a similar approach, is based on notching the time reverse trajectory so that its perturbation is essentially proportional to the adjoint field. However, what you can see here is that when you want to generate time reversal in this overdamped system, you would need to swap the sign in front of F, right? You would need to make, you need to turn plus F into minus F. That will generate time reversal. On the other hand, the adjoint, however, is damped. So the main point here is that even if you were able in your hardware to turn damping into gain or vice versa, you could still not run an experiment to get the adjoint field, because the adjoint field fundamentally requires damping. So there's a contradiction, and then what you're left with in this case is equilibrium propagation. I think by now it's well known that equilibrium propagation can also be derived from the adjoint method. Yes, so exactly, so that across all systems, linear systems require Onsager reciprocity, and nonlinear systems require time reversal upon an operation solely on the final state, and these two conditions are independent. You need reciprocity of the Jacobian. You can have time reversal symmetric systems that are, however, not reciprocal. So you need both to extract the adjoint field gradient in the nonlinear case. And then how do you do it? Well, for the linear case, it's a finite amplitude construction, no notching, a single experiment. In the nonlinear case, you do this difference of trajectory and notching around the time reverse trajectories. So what systems do we cover? We cover first order, as I discussed. We cover second order real system. We also cover complex valued Helmholtz equations. This includes integrated photonics. And we also cover complex valued Schrödinger equation, which includes diffractive free space optics. And so going back to this slide, we actually can rederive all the learning methods from all these papers using the adjoint method. The one with the brackets are sort of self-learning in addition, which is something we don't cover. And so we're about to be finished with the paper and loading on arXiv. It's coming soon. A lot of work was done by Yitan, the student of Hakan, and Ryan Adams is my own advisor. Thank you for your attention.
Questions? Don't be shy.
Yes.
For the great talk. I had a question about reciprocity. So could you further generalize this by also allowing local symmetry operations like Nicolas showed?
Yes, so I actually have an extra slide on this. And so in principle, what the general condition is that there needs to be a positive definite symmetric transformation so that you get the transpose from that transformation. And then you can sort of propagate the V-weighted adjoint field. But you need this, like, practically, this means you need to know V and you need to be able to apply it.
Sure,
so
sure.
that I think is practically harder. Yeah. And in the nonlinear case, it's the same thing. So that basically means that F can be V times the gradient of an energy, I think, in most cases. Yeah. So generalized gradient flows.
So yeah, this is very interesting indeed. But I mean, I assume you compute these gradients, and when you talk about implementing something like this in real hardware, at this point you have to make a change in the parameters, correct?
Yes. Yeah, so that's actually a good question. So my impression is that in nonlinear systems, this will be extremely hard. But in linear systems and with these recent proposals of encoding the input into the parameters, you have a much simpler algorithm. You have this finite amplitude algorithm. You don't need to have time reversal. So you could also exploit gain because this is also, you can have gain and loss, and yet you have reciprocity. So I think using these nonlinear parameter encodings together with like on-device gradients is probably the practical way forward.
Thank you. Let's move on to the next talk. Our next speaker is invited, speaker Daniela Markovic, and she's going to talk about quantum neuromorphic computing
How do we do this with here?
with superconducting circuits.